Alright, so what we'll do in the next few classes is let's go back and recall so we started with the two-body problem, right? And when we looked at the solution, this was a solution to two-body problem. If you see here, as I mentioned to you, this is the problem is expressed as a differential equation, second order differential equation, second order nonlinear differential equation, and the solution is a algebraic solution in true anomaly. Okay, so the limitation is we cannot determine R as a function of time. So let's look at this, and if you were to figure out R at different time instances, what do you need to know? So here, tell me what are the variables in this solution to two-body problem?
R,
H is not a variable. H is a constant, right? It's conserved, so it's constant. So if you were to write only this, R is a variable and theta is a variable. Okay? Only theta is varying, and because theta is varying, R is varying. See that? Okay. So how do we figure out? See, if you want to keep a track of where your R is, you cannot keep on measuring this theta, right? In reality, you cannot keep on measuring this theta every time you need to know R. You need to develop a function. So if you just input time, if I know this is the time, I know where my time is. That's where we are going. So we introduced the concept of eccentric anomaly. Okay? So we know what true anomaly is, right? What is true anomaly? How do you define true anomaly?
R cross B.
What are you saying? R cross B is true anomaly?
No, that's not it.
true anomaly is where
If I ask you to define true anomaly, what will you write?
the angle between the distance and
The angle between pair is a pair.
Right, it's the angle between.
When
When you determine theta, what formula did you use? You remember what formula you used? How do you determine theta from orbital from R and B?
Also, I reverse it. R dot E over R E.
Right. So what is that R and E? R is the position vector of the satellite, right? And E is the eccentricity vector, what is the perigee direction. Okay. So if the angle between the perigee direction and the direction of the satellite. So if you look at what true anomaly is, you want to simply represent true anomaly pictorially. So let's say the satellite is here. And what would this be? So this is that P direction, or this is also E direction. Okay. Got it? And what is this point? This is your focus, center, and unoccupied focus. And what is this angle? And this is the orbiting body. What is this angle? That is a true anomaly. Okay. And this is, what direction would this be? What direction do we know this as? I would say this is the R direction, or we generally use this UR direction. Okay. So you can say the true angle is the true anomaly. This is how you define true anomaly. R dot E is equal to R E cosine theta. Okay, so this implies theta is equal to cosine inverse R dot E divided by R. Okay. Now what we do is we introduce this eccentric anomaly. What this eccentric anomaly does is you circumscribe a circle around the ellipse. How do you circumscribe a circle around a square?
You say what?
Circumscribe. Circumscribe, inscribe. You know what circumscribe is?
No.
This sounds familiar, but it's not right.
So circle. So if you have
Gross.
if you have this, if you want to circumscribe a circle around this, what you'll do is you'll find the center, okay, and using this as a radius, you draw a circle, okay. So this is your circumscribed circle, right?
When they try to teach us that 200.
Huh?
I say yeah, they tell us that 200 didn't work out too well.
So the important thing is to remember is the radius is the half of the diagonal. Okay. How do you inscribe?
I have to try to understand that. You
Huh?
draw to the middle.
Huh?
You draw to the line to the middle.
Right. So the inscribe would be this radius
This is the top.
because it comes inside. You got it? So you understand the difference between inscribe and circumscribe? Circumscribe is. So how do you circumscribe a circle around the ellipse?
So your radius is going to be your perigee difference? Or
The radius would be And what is the, if you inscribe, what would be the diameter?
It would be the minor axis.
Minor. So what you do is, you take this radius, okay, and you circumscribe it. Alright. Now what we do is, we draw a perpendicular passing through this point. And wherever that point meets the circumscribed circle, you join that point to the center. And this is the eccentric anomaly.
This is
Is it clear what eccentric anomaly is? First, understand what true anomaly is. Okay? Once you know what true anomaly is, what do?
we'll make a circle around.
You circumscribe the circle around the ellipse, and then you draw a perpendicular passing through the position of the orbiting body. You draw a perpendicular, okay, and wherever the perpendicular meets the circumscribed circle, you join that to the center. And the angle made between this line and this line is that eccentric anomaly. So here E is theta is true anomaly, and then E is eccentric.
Let's see.
What is this distance? Semi-minor. It's B, right? What is this distance?
It's the radius.
Huh?
It's the radius of the outer circle.
Oh,
What is
we
it?
just
Oh,
compare
it's-
the ellipse to the.
So what is it?
It's A.
So this distance is A. Got it? Because this distance is A. Right? Has to be A, and what is A here?
Semi-major.
Semi-major axis.
What's the point of this?
Hmm?
What's the point of this?
That's the reason you should come early. Okay?
Okay.
What we did was, we had talked about this in last class as well. We have discussed the two-body problem and the two-body solution to the two-body problem. Okay. Now, if you look at the two-body problem is a second-order nonlinear differential equation. The solution is an algebraic solution in theta. We are looking for a solution. The limitation of this is R cannot be expressed as a function of time. You understand?
I was just saying in real life situations.
Hmm?
I was just saying in real life situation.
That's what the real life situation, when something is orbiting around you, if you look at the time, you should know where your satellite is. That's how you want your solution to be. That's how you would want, if you are, let's say, if you want to weather a pig, if you want to track the space station, or if you want to track your satellite, you look at the time and you figure out, okay, this is my satellite should be here, my satellite should be there. So from this we cannot do that. Okay, so that is the reason we are trying to do. I'll name this. So here, let's call this O, F, and let's call this point as V, and let's call this point as P.
That's a V.
That's V, yes. O, F, V, P. I'm just going to develop this relationship. And this point as S, and this point as Q. Okay. Now, if you want a better view of this, this is figure 3.3. Page 149. What is this distance?
The radius.
Right. So what is that distance?
Right.
Huh?
P, 0 to P, O to P. Well, you're right.
It's A, right? Is it still A?
Yeah.
Right?
What was that about?
Because this is the same distance as this. It's a circle, right? So can I write this? Just tell me, look at this derivation and tell me if I can write this. A cosine E is equal to AE plus cosine this distance is AE. Okay. What is A cosine E?
Wait, what? What is A cosine E?
Mm-hmm. What is cosine E?
Got an angle right there. E angle.
It's this distance, right?
Yeah.
Divided by this
to
distance.
B.
See, O to V, OV divided by OQ, right?
What do you see Q?
This Q. A cosine E is this distance, OV. You agree?
Yeah.
But this distance is equal to this plus this,
Gotcha.
right? This is always AE, the distance between the center and the focus. Okay? And you can prove this to yourself. And this distance,
It's R cosine theta.
it's r cosine theta.
So that's why we need to.
Yeah. So that r cosine theta also makes sense, right? Because if you look at this angle, this triangle, this is theta, so this is r, right? So write this as equal to AE plus A into 1 minus B squared. Tell me what did I do here?
Oh, so you plugged in the different equation for the equation for A, R.
I plugged in the equation for R here. I just put in the equation for R. Okay. So this A, this is H square over mu. A into 1 minus E squared is simply, so if you write this as, does this make sense?
Yeah.
You can write this as AE plus A into 1 minus E squared cosine theta divided by 1 plus E cosine.
Ouch.
Okay. And if you simplify this,
What happens to the cosine E?
huh?
Oh, you just go on one side. Never mind.
Cosine E is as it is. So what I can do is I can write this as cosine E is equal to E plus
R.
1 plus E.
Yeah.
What did I do here? So if you write this again here,
You divide A.
yeah. Here this is 1 E plus E square cosine theta plus cosine theta minus E square cosine theta divided by 1 plus E cosine theta. So this cancels with this. This will end up with E plus cosine theta divided by 1.
Distributing that 1 minus B squared cosine theta, shouldn't it just be cosine theta minus B squared cosine theta?
So here I multiply this with this because you have to take this thing, right? So you get E plus E square cosine theta plus cosine theta minus E square cosine theta. So this cancels with this. Okay. Now I can write this as minus E square. you have to just use the identity sine square e plus cosine square e is equal to. Okay. To get this. Any doubts? Any questions? Huh?
What at the bottom equation? Wouldn't that be E, not one?
This one?
Yeah. Wouldn't that just be E?
No, because you're using the E would be like A equals the sine square plus cosine square is equal to
You know what this identity is?
Yeah.
This is a universal identity. Whether you put it for e theta, sine square theta plus cosine square theta is what? Always 1, right? So you apply it for any angle, it will be 1. That is that identity. So what you can do is, so you can just think about this.
E is an angle.
Sine square theta sine square e is equal to 1 minus, I'll substitute this whole thing. Okay? You have sine square e is equal to what? 1 minus cosine square e, right? 1 minus, you have e plus theta, e plus cosine theta square divided by 1 plus e cosine theta square. Okay? This is okay? So this would be 1 plus e square cosine square theta plus 2 e cosine theta plus e square, oh sorry, minus e square minus 2e cosine theta minus e cosine square theta. I've expanded this, divided by 1 plus e cosine theta square, right? So if you have 2e cosine theta, 2e cosine theta cancels out, okay? And you have 1 plus e square cosine square theta minus e square minus cosine square theta divided by 1 plus e cosine theta. This is equal to 1 minus cosine square theta minus e square 1 minus cosine square theta divided by 1 plus e cosine. So this would be 1 minus cosine square theta into 1 minus e square. What is 1 minus cosine square theta?
Sine squared.
Yes. And this is what? Sine squared E, right? So now sine E would be square root of all of this. So it will be square root of 1 minus E square sine theta divided by 1 plus E.
So that's like
That's how I got that. Okay. Now what we'll do is, to erase this, tangent square E over 2 is equal to sine square E over 2 divided by cosine square E. This is equal to 1 minus cosine E divided by 2. Okay, 1 minus
What is the end game? Like, what are we trying to get to? What are we trying to get to approve?
I told you, have some patience.
Okay.
Yes.
why did you divide E by 2?
So what I'm trying to do is, alright, here is the end game, okay? Or part of the end game. We'll express theta in terms of true anomaly. We'll find the expression between the true anomaly and eccentric anomaly. And then we'll find the expression between eccentric anomaly and time. You understand? Then you can convert true anomaly to time.
I gotta see it laid out. It's laid out.
So you have tangent square E over 2 is equal to 1 minus cosine E divided by 1 plus 1 minus sine E. Substituting expression for cosine E and sine E, you get tangent square E over 2 is equal to root of 1 minus E divided by 1 plus E. Alright, does this make sense? If you substitute, so we had an expression for cosine E, right? In the initial derivation here. And we had an expression for sine E. And the expression was in terms of, look at your notes. You just did it. What was the expression for cosine E? It was expressed in terms of theta, right? And again, this was also, we expressed this also in terms of theta. And if you substitute and simplify, you're going to get what you have done here is you've found a relationship between theta and E. You've expressed true anomaly, you expressed eccentric anomaly in terms of true anomaly. Okay? And this is the first part of that end goal we are talking about.
If you're substituting cosine E and sine E, wouldn't that just be tangent of E over 2? Still?
No. You substitute cosine E, look at the expression you have for cosine E. It's all in terms of theta. That is, E gets, look at the expression. So for example, look at the expression here. This sine E is expressed in terms of theta, and that's what I'm going to substitute here. And that's what I'm going to substitute here. And if you simplify, you'll end up with this. Okay. And this is this will call Kepler's equation. Okay. Now keep in mind, Kepler's equation and Kepler's laws are different. So what is the point of Kepler's equation? What is the objective of Kepler's equation?
To have E and theta in the same.
Express E in terms of
Theta.
theta. So here, what are the variables? What are the variables?
E.
E and theta. Right? If theta varies, E varies. This E is what? Eccentricity. This is constant, right? For a given orbit, this is constant. So what we have done is we have expressed theta in terms of E. Next class, what we'll do is we'll look at expressing
E in terms of time.
So now can you relate what we are trying to do?
I got it. I just, impatient, like you said, right?
Yeah, we have to do it. We have to do. This is how we develop understanding. This is how we advance our understanding. Okay.